Hi everyone. So in this video I'll be showing some of the things I've been doing with using Nephio on Proxmox, and I just want to share a sample architecture that I'm using on my home lab. So Proxmox is quite common to an extent, and it's something that I find it's a bit easier for me to use for my home lab server. So through it, I've been able to practice some of the cloud native projects or 5G or telco architectures or designs or POCs, right? So I thought of like, okay, so how can we make use of Proxmox and then for deploying Nephio? And from this architecture, you see, though it's based on Proxmox, but it's most likely it's also something that will work just the way you have it with normal virtualization or hypervisor platforms. So let's go into it. I'll be going briefly into the architecture, the reason why I chose some of the components, and but the actual deployment, I might do that in another video. So first of all, for the Kubernetes cluster, I'm making use of the K0S Motron, or Cosmotron, I call it. I don't know if that's the right pronunciation, but it's they provide the ability to run Kubernetes control plane as pods, right? And one of the advantages of this is especially when it comes to the edge location. So you can take a look at the project, but I'm not going to go deep into this project. But essentially what it's providing, what I'm using it for, is that I have a management cluster which is also built by running on K0S, and then from there I'm now creating what we call the hosted control plane. So the hosted Kubernetes control plane is whereby you are not running the control plane alongside where you have the worker nodes, right? And this is true in most cases, like I said, when it comes to the edge locations, or maybe when you have the telco 5G sites where you have maybe like your DUs or your CUs or things like that, whereby you could fully maximize the servers that are in those edge locations. So instead of dedicating servers for the control plane, and you need the control plane to be highly available also, and by that you need a quorum, right? So it's that you go from 1 to 3 and 5 or thereabout. So it has to be a odd number because of your HCD node. Although there are some other ways you could do that, but ideally you don't want to run one instance of your control plane. So if you could have a hosted solution like this, then this can give you a bit of more freedom in, like, you could just deploy, like, for instance, maybe you could just have like two worker nodes, right? In some cases where you are constrained to have 2 worker nodes, then fine, then you can this kind of architecture can be of benefit. So in this case, you see that I have a management cluster, and in this management cluster I'm having the hosted control plane mode. The hosted control plane. So each of these API pods is for each of the 5G core workload clusters. So I have like the 5G core, you have the 5G edge, and then you have the 5G regional stuff. So here it's being exposed as a load balancer. So once this is created, you get to use it as a load balancer. And in this setup, I'm making use of Metal LB for the load balancer, right? So each of these, you can see I have 3 pods, and each one of them is connected to this worker node. So that's an example of, I know some of you already knows this, but for those who don't know, this is another alternative stuff. So, but quickly to see one of the other side to this kind of architecture is, now you see that you need to pay close attention to this cluster, because now it's not just hosting some other controllers. That's actually where you have your Kubernetes control plane for the remote clusters. So in this case, you can really go for high availability, right? In most cases, it could be a multi-zone. You definitely use a multi-zone kind of deployment if you are making use of a cloud architecture, right? And if it is still on-prem, you could have this like in a central location, right? And then you have the flexibility. In that central location, you definitely have a pool of more servers. So in that case, you would have a high resiliency and high availability. So, but then it also brings a bit of more management efforts to make sure that this does not go down, because once anything happens to this, then it's going to somehow affect the workload clusters. But if you have this control plane in the, like I said, in the edge locations, your control plane will not be centralized. So if one goes down, then it will not affect the others. But then, like we said, it also has its own maintenance overhead, right? Because you now have more physical servers, maybe dedicated for the control plane, and also it could, in terms of cost, like I said. But so depending on the kind of architecture or the kind of requirement that you need, this architecture might be an advantage, and in some cases it may not. So for each kind of requirement, you need to really do a good analysis to make sure that you are selecting the right architecture. But for this was a challenge for me, just to see how it's going to play out and to see whether it's possible. So the management cluster is this. So if I could show you some of the how it looks like. So let me go back into the cluster. So now we are in the management cluster, as I said. So if we look at the pods at a glance on the management cluster, so you see I have namespaces for the regional, for the core, and for the edge. So you see on the core side, you can see that for demo purposes, I'm just running an instance, one replica of the control plane and the etcd. So these are running as stateful sets, as you can see. So you see here that this is the core control plane, and then this is the etcd that it's making use of. The same thing for the edge, and then the same thing for the regional. And if we move out of here and we check the services, so we'll see that it's we see that we have 3 load balancers. So you can see one in the region, one in the edge, and then one in the core. So you see each one of these is feeding back to the to each of the clusters, the worker nodes. So now let's move on. So if you want a bit of how Nephio works, you could check the Nephio documentation. So, but in the management cluster, essentially, when you install Nephio, you have Nephio, and then you have your porch, right? So porch is the one that will actually you'll be interfacing with to create the package variants or package variant sets, which we in turn will clone the packages from as blueprints from an external repo, and then it will now push it to each of these repos. And each of those repos immediately pushes it there, then the GitOps tool will pick it up and then will deploy whatever things you want it to do. Now, another component that we'll be looking at in this is that all the configuration, as much as possible, I've tried to make use of Kubernetes custom resources, so that even your site routers or your central router, in this case I call it like the MPBN router because I couldn't find another name that suits this. So the MPBN router in this case, it's like your backbone router that connects all these sites together, and it centralizes the communication. So in this instance, I'm just using a vGenius, a virtual Genius router lab, the lab edition, which is available for lab use cases. So, but this Juniper router is actually configured by this project called the SDC controller. So this is actually it's making use of what do you call it, netconf. And with the netconf, it's able to translate Kubernetes YAML into the netconf stuff, and then it will now configure this router. So an example of the configuration for that router, as we'll see, and where is that? So let's see. I think I've not created this as a package variant, but let's see. Okay, yeah, the remotes, not the remotes, the SDC package. So I can't go through all the steps for the SDC. You could also check the website, which I will shortly show. But then if you look at the configuration here, you see that we are actually making use of a Kubernetes custom resource. So is the name, and then you see all the configuration, right? We are creating VLANs. Then, I mean, this is how you also create your normal Junos interfaces and stuff. We are making an interface, the trunk, which I'll show the network configuration. And then, I mean, the network design. Then you have the routing instances, right? We have one for the N2, N4, E1, the F1, and all the like. So if you apply this to your router, and then if you come back to the Junos, so this is the Junos router, which is also running as a virtual machine on Proxmox. So it's a telnet session. So let's see. So this, let me see. Okay, this was working before, but trying to see why. Okay, so let's do this. Maybe the other session I had was not properly closed. Okay, I'll probably check that later. But subsequently, I had this open, but not sure why it was. But you can see here that I actually was connected to it before. But then if you do the show configuration here, you can see that it matches what I have in the YAML I just showed you. So you could see the interfaces. The G01/0/1 is made a trunk, and then you have the VLAN members, and then you have the IRB communication. That's the layer 3 the layer 3 configuration for the VLANs. And then you have the routing instances, E1, F1, N2, N4. And then you have of course, each of those routing instances have the BGP configuration, which will be speaking with the site routers. So if you want to have a look at the SDC site, so this is the SDC page. So they have a configuration already they have a support for Juniper, which was okay for me. It was exactly what I was looking for. So this is a good project, and they also have another project based on it called Kubernetes, which I've not tried, but it's something also that is related to this software. So now, what about the site router? So I consider this like a location, just as you have it in the way you design your telco networks, right? So yeah, I'm trying to make use of an example here. So instead of having dedicated sites, I mean physical routers, right, which might be an overkill for some of these locations, depending on your requirements. So in this kind of situation, if the router that is required is not, you don't necessarily require it to be like a physical device, right? Or even a virtual machine. You could have some of these vendors, some of the networking vendors already have a containerized version of their routers, right? So an example of this, which I'm making use of, is a combination of FRR and VPP. And FRR and VPP already they have a good support for container images, which can be used. So in this instance, what I'm actually making use of both FRR and VPP. So FRR will be where the BGP will be running, that's the control plane, and VPP will now be the data plane. So you see, each of the site locations have a pod, and the advantage of this is that you can make use of the same worker node that you have running with for the CNFs. You can make use of it to actually deploy your routers also, and the routers then will now be connected, in most cases via fiber or the backhaul communication back to the MPBN router. And then you see in this kind of configuration, you see from the core what is actually needed is the N2 and the N4, which the regional will need. And then so the regional, the CU CP will need to communicate for the N2 to the AMF, and then the UPF in the edge location will need the N4 to communicate with the SMF. And then also from the edge location with the regional, you also need the N4 also to for that communication with the SMF. The F1 and the E1 is for the DU and the CUUP to be able to communicate to the CUCP for the RAN communication. And to configure this, the FRR and the VPP. The VPP is just like I said, it's just a data plane. So to configure the FRR, there is also a new project which I also checked by the people that created Metal LB also. So it's called FRR K8S. So FRR K8S is a project that enables you to actually configure to be able to configure your FRR using Kubernetes custom resources. So in that case, you can say as an example here, you see they're actually making use of a YAML file to configure the the FRR that are running on these cell sites. So in this situation, it's actually they are running as a daemon set. So once this daemon set they are deployed to these sites, then you can make use of your the FRR K8S to do the configuration. An example of that is, and it also supports if the current YAML format does not give you what you want, you can actually pass you can actually pass the full-blown configuration, and it will do that. So the example of that is this. So we see that we're actually making use of so I'm trying to recollect the raw config. Yes, so you can actually use the raw config, and the raw config gives you the full syntax in case it is not yet supported. So in this example, I'm actually making use of the raw config. So you can see here that in this package variant, we are actually each of the cell sites each of the 5G location has their own configuration. So like the edge, if you recollect, the edge needs like the N4, the E1, and then the F1 VRF. So I'm making use of a VRF configuration also, and that will take care of the communication. So on the install, on the site router installation, or I call it deployment, this is where you also create, you need a base configuration for the VPP. So for each of those sites also, you need to create, this is just creating it's creating the VLAN interfaces, and then it's assigning it to the VRFs or routing instances, as you may call them, and then it's setting those VLAN interfaces in the right VRFs, and then also I'm making use of the LCP, the Linux Control Plane project. So the Linux Control Plane project on the VPP is to facilitate the making use of FRR as the control plane to sync the routing table, as FRR is receiving it via BGP, to now sync it to the VPP. So the VPP is essentially just a data plane, but the LCP project is what facilitates this. It's doing the communication between the control plane, which is running in FRR, and then with VPP. So yeah, with the LCP, whatever IP address you are setting here will actually reflect also in your FRR by the time you do that. So all these interfaces that are created here, by the time you go into your FRR, you actually see them also as an interface. So for today, I mean, because of time, I may not go through all this, but I'm just trying to go through some of the high-level design consideration. So that's that about the FRR. So you can also have a look at the project and see. I opened I opened an issue there also to kind of like to suggest some of the because currently this is running as a daemon set, right? So in some cases you may not want it to run as a daemon set, and for instance you just want it to run on a particular, maybe as a single, or you want to control how many replicas is running. So the creators of this of the FRR KTS, I think they are also interested in that. So we'll see how that goes. So let's quickly go back to the configuration. So that's how. So the essence is to show that even your network configuration can be done using Kubernetes as a control plane, and also your site routers can also run as a container, as containers, right? This can free up the additional equipment that you need. So instead of having a dedicated router, you could also have it as a container, depending on the use case. And don't forget, like I said, the whole concept of the hosted control plane, also how it ties back to this. So let's also quickly see the actual design of how the Juniper and then the FRR are communicating. So you see, this is the MPBN router, which is a vJunos, the lab edition. So you can see that this is an interface, and then we are creating multiple VLANs, right? So you can see like VLAN 200 is on the Junos router, is tied to the VRF N4, right? And then you have the autonomous system here. So you see that each one of them goes to not only VLAN 200 and VLAN 204. Each one of them is used to communicate with any other thing. Like you see the N4 here. N4 by default, N4 which CNS require N4. That's the UPF and the SMF. So that's why I'm using two VLANs, right? So 200 and 204. And then you see that this also the same I'm using the same color to make it a bit easier. So you can see here that this is the edge cluster. So that means this is the UPF. So essentially, this is the site router, which I say is also running as a container, right? So there is an interface between the site router itself and the UPF itself to make it like the default gateway. I mean, the gateway in order for it to reach the SMF. So, and then there is another interface that the site router will communicate with to the MPPN router. So it's good you could take a pause in this part to actually like go through it, because if you look at the color coding, I think it will make more sense. So you can see the E1, F1, N2, N3, I mean N4. They are having their different VLAN configuration, and then on the Juniper router, and then the same also goes to the site routers. So this is essentially how they are tied together in terms of the VPP and the VLAN configuration. So the BGP is configured as eBGP. So I think that was the easiest way I could do to make this work like seamlessly, so that the route could be exchanged without much configuration. But this requires a lot of planning. As you can see, the IP details, I mean the IP configuration needs to be well thought of before you do this. But if you understand the flow, you pick it one by one, and then you'll be able to do this. And if you check the Juniper configuration also, it actually flows back to what we have here. And you can also have a look at some of the files here in the Git repo. So I'm not sure if I've posted the one for the site router. So no, I mean for the Juniper router. So I have not done that, but I can do that. But you can still see. Let me see if I've pushed for the site routers. Okay, so no, I think I'm in the wrong. Yeah, it's in the R3 branch. So let's see the R3. Have I pushed something there? Yeah. So you need to go to the R3 branch of this repo here for the Nephio release 3. And if you go to this, is where you have, like I said, the configuration that I showed you. So you see exactly what we have here is it maps back to the diagram that I have here. So I just created this diagram just to show you how the configuration works. No, so there is no need for that. So like I said, and also the NRF requires, the UPF needs to communicate with the NRF. So the NRF is also running as a load balancer, and it's also making use of Methyl LB for that communication. And also, I make a note here that I'm using a flat network. This is just for demo purposes, like I said. So even though I'm simulating like the site locations, but the Kubernetes primary interfaces, they are hooked up to a central, the same bridge on Proxmox. That's VMBR1. So essentially, it's like a flat network for that. So they can. It's easier for them to communicate. In a real world scenario, that would be a different thing, but I didn't want to really focus on that. The main routing I wanted to focus on was the protocol interfaces, which I already have shown here. So that's that for the for how the configuration looks like. So in subsequent videos, I might do some more deep dives to see how these components can be set up. But this at very best is just to show you how you could make use of Kubernetes as a control plane, not just for normal, for your usual 5G CNFs. You could use it to actually also configure your site routers. Your site routers and your MPBN routers, and also you can make use of the hosted control plane. Now, one thing I forgot to show is that on the worker nodes, you can see here that the worker nodes also they are communicating via a VLAN. So you can see here that this is a VLAN 102 or 104 with the VPP. So if this is a VLAN interface, definitely the CNFs too will need to communicate via a VLAN. So otherwise, it won't work. So I also try to automate the VLAN, the actual VLAN configuration on the worker nodes. So what I did for that is you could, I think maybe it's easier to show it from the Git repo. So if you come to this, you can see the VLAN interface package. You can see there is a daemon set. So what this daemon set is doing is to actually pick up a configuration file, and the configuration file, you see where I'm saying a VLAN config and then the VLAN parameter. So the reason this is your Porch package. So this is like your templates, which once we now create a package variant, it will now deploy it on each of those worker nodes. So if you go to the package variants section, and then if you go to this the VLAN configurator, so you can see for the edge location, right? I'm changing the VLAN parameters, which you see, which you saw from the package. You can see that now I'm saying, okay, I want to create these VLANs on this interface. So with that, it's also, you don't need to pre-create this maybe using your user data script. You could, that's another way. But then what if you want to have a change for those VLANs? So in most cases, you will have to redeploy the worker node or have some other way to do that. But one of the ways I just wanted to try is to use a daemon set to actually do the configuration. So the daemon set will read this configuration file, and then it will now create these VLANs across this. It will now create the VLANs on these interfaces. So let me see if we could go through one of the worker nodes. So let me get the IP address of one of the worker nodes. So let's say regional, and then let's say get. Let me do so it's on 20.1.10. So if we open another, then I think it's, what's the IP again? That's 110. So if you do an IP address, so you see so you see the VLAN interfaces. So what I did was to make the interfaces look a bit unique. I give it to start the naming convention with ML, multus, then underscore this, so as to make it a bit different from to show that, okay, it's the VLANs we are creating from the daemon set. So if you look at this the links, you can see this is ML. So there is a command, if I remember, link show, that it will tell you is it I can't recollect. So there is an IP command that will actually show you the VLAN configuration for that particular interface. So I just want to I can't recollect the command now. If I can get that, let's see. -D, I don't think there is anything -D. Yeah, it's -D. Yeah. So here you see, I just want to confirm so that for you to be sure that it's actually a VLAN interface. So here you see that this interface, you can see the VLAN 802.1q, and then the VLAN ID is 108. So, and then it ties back to the ENS 19 interface. So that'll be it for now. So subsequently we might do, like I said, we might do a deep dive and see how this is configured end to end. So can have a look at the projects I've mentioned, and you can but I didn't give a link. You could check the VPP also for the LCP project. That's the Linux control plane. That's the only one I think I'm not showing, but the remaining one, the Cosmotron, the SDC, the FRR K8S, and then Nephio itself, you can have a look at it. So for your information, I think this was done with the Nephio release 3 for those who are who may be wondering about that. So thanks for watching, and see you in the next.